morning and welcome to Kung Fu Physics. This is a very early morning or late night edition. Today is the day of the 2012 annular eclipse. So maybe you'll remember where you're at when that happened. You probably won't remember where you were at 3:30 in the morning that day because you were probably in bed sleeping. But what I'm going to be doing is number 78 off the 1992 exam. 78 off the 92 exam. It's a lengthy problem, and so I'm going to have to talk fast and move fast through this one. It's a classical mechanics problem, but it's tricky. I wouldn't call it an easy problem. I wouldn't call it a particularly hard problem. It is potentially a time sink of a problem there. So I'll hold it up. This is going to be a little fuzzy, so hopefully you have these printed off and have it at home as well. It looks something like this. Hopefully you can follow along at home. Number 78 off of the 92 exam. As usual, I would scan the answers briefly. Answer A is interesting because it is fairly different. I would be hoping doing this problem that I could eliminate that or choose that answer rather quick, but just looking at that, it's some type of equation of motion for something, and I can't eliminate anything other than that or really gain that much more information. So a quick scan of the answers, and then I would be into reading the problem itself. Quick glance at the figures. 78. One ice skater of mass m moves with speed 2v to the right, while another of the same mass m moves with speed v towards the left, as shown in figure 1. Their paths are separated by a distance b at t equals 0. When they are both at x equals 0, they grasp a pole b of negligible mass. For t greater than 0, consider the system as a rigid body of two masses m separated by distance b, as shown in figure 2. Which of the following is the correct formula for the motion after t equals 2 of the skater initially at y equals b over 2? Okay, so conceptually, quick, we realize what's going on. The two skaters are coming together like this. They grab the pole. At that point, they're going to be moving together. Conceptually, we can sort of reason rather quickly that they're going to be moving together that way because there's going to be some linear momentum left over, and because there's angular momentum, they will also be rotating. We want the motion of the skater up on top, and so in our head we are envisioning this guy or girl going something like that, in that direction. Conceptually, we could knock out A at that point already and even make a guess if we were so disposed to do so, but we'd like to do a little bit better than that. How do we do that? Well, we have to use, what's important is conservation of linear and angular momentum in this problem. I'm not going to rewrite the figures. Hopefully you're looking at them in front of you at home. But for me, it does help, rather than looking at figure 2, to make a mind's eye simplification here of a mass. In this case, it would be 2m. So I imagine this mass of the skaters together like this. They have a moment of inertia I that I will need. They're going to be rotating at rate omega, and they're going to be moving with velocity v prime. I'm going to use a prime there because we already have a v in the problem. A simplified version like this might help you. It helps me visualize this, and so I would love to be able to know what is the velocity v prime of the center of mass of the two skaters. What is their omega of them rotating? These would be nice things for me to know to assist me in choosing an answer out of those equations of motion that are presented to me. So v prime comes out pretty readily, actually. Just by looking at the problem. I'm not going to muss with the details here. I want you to kind of do it because for the physics GRE, be careful, but get away with what you can doing in your head. So I'm going to kind of do it in my head, so to speak, to get the initial linear momentum. I have one mass going to the right at 2v, and I have one mass going to the left at 1v. 2 mv going that direction, 1 mv going the other direction. So what's left over is mv going to the right is going to be my initial angular momentum. That is equal to my final angular momentum. This mass, which is 2m, multiplied by v prime. Real quick, v prime pops out of that. It's v, well, I'll write it in here, mv over 2m equals v over 2. v over 2, so that is my transverse velocity of the center of mass. It is the transverse velocity of the skater as well. Or in other words, I'm going to have that multiplied by the time, and that is going to be in the description of the x component of the motion of the skater. That has to be in the description of the motion in the x-axis of the skater. And so I could, at this point, go back to my answers and eliminate 2 more answers as well, because B and D do not have 1/2 V, or V over 2. They just have V times T. To me, that seems pretty straightforward, that I recognize that as being incorrect. I know that my answers are now, at this point, down to C and E. In order for me to distinguish between C and E, it seems to me that I need to get omega. And so to get omega, I compare my initial angular momentum to my final angular momentum, which is just I times omega. My initial angular momentum, again, looking at the figure and plucking this off of the figure pretty quick here, the angular momentum caused by the 2 skaters is going to be the okay, I'm having a brain freeze here. It's going to be the radius cross the momentum, r cross p. L equals r cross p. Because they're at 90-degree angles, we don't have to sweat that too much. Really, we're just going to be multiplying it. But it's r times p, which is b over 2, times the first skater is m times 2v plus, and so this is my total initial angular momentum, and that is so 3mv times b over 2. Okay, I'm sorry, that is very kind of smashed at the edge of the board there, but this is my angular momentum. Okay, so that is equal to I omega. And so if I want omega, I just take 3mv times b over 2 and divide it by I. So what is I? You get I via the parallel axis theorem. And reviewing parallel axis theorem in a wiki search or getting out one of your old textbooks is a great idea, because you'll run into parallel axis theorem in other practice physics GRE problems. No question about it. For some reason, the test makers love the parallel axis theorem and making you calculate those moments of inertia with it. So basically, it just says that if I'm taking a given point and calculating the moment of inertia of a bunch of particles around that point, each particle adds the mass of that particle times the radius from that point that I want to calculate the moment of inertia times the radius out to that mass, mr squared. That's how it sticks in my head from freshman physics all those years ago, mr squared. So important to do that. In our example, or excuse me, in our problem, we just have those 2 particles and they're the same. They are m. They each add the they add a value of m times b over 2 squared. So I would just get 2 of those. I equals that. Okay, so 2 m b squared over 4 whatever. Okay. So we would simplify this to get omega, and omega equals 3mv b over 2, blah blah blah. And you know, I'm writing this out, but we want to save as much time as we can. If there are some shortcuts that you can use, by all means do them. I'm being a little sloppy this morning as far as time goes, but I get my omega as 3v over b from that. That is certainly in the answers. The omega goes, you know, you have omega t in circular motion inside the parentheses of your cosines and sines there. So the amplitude of the motion is on the outside. So looking between C and E, the omega that I just calculated is present there in answer C. I see 3vt over b, or omega equals 3v over b. And so I would choose answer C as the correct answer. And that took me a little over 10 minutes. I shoot for 10 minutes with most of these videos because my thinking is that if I someday want to be able to do most of these problems in 2 minutes or less, I should be able to explain and walk through what I'm thinking on these problems in something like 10 minutes. But this one, like I said, is a potential time sink, and could really trip you up, taking more time than you like. It's taken me more time to explain it than I would like, and it's a little tricky. I looked at the popular website out there that has solutions posted, and there were some other interesting ideas on this problem there that are probably worth scooting over and looking at, maybe a little differently than the way that I've solved it here. There are certainly other ways of looking at this problem. So there you go. That was number 78 off of 1992. Study hard. Best of luck. See you next time.